Now we have our next speaker, and I have to admit that I was pretty looking forward to this one because to this topic because it's closer to my area of interest, to security. And we have the privilege of having someone who is not only involved in the, let's say, security part, but lately also some involvement in the F1 component, so congratulations for that. Next we will talk about Bitdefender. We will talk about Bitdefender's framework to ingest, process, and visualize security-related events and analytics data, which is called Karma. Compound a number of node.js microservices, multi-node Elasticsearch clusters, Kibana plugins, which actually all of them ingest a very high number of ops and security and storage, hundreds of terabytes. Okay, compounding everything together in security, it's very, very, very interesting and highly important. Joining us to share the architecture and scalability steps they took to support this vast amount of data is Octavian Rinciog, senior software engineer at Bitdefender, a professional with more than 10 years of experience in building scalable systems, who was involved during his career in many projects dealing with a lot of big data technologies and architectures. Without further ado, Octavian, you have the stage.
Thank you very much. Thank you very much for the warm presentation, Daniel. So, yeah, today we'll be talking about how to scale Elasticsearch cluster to store hundreds of terabytes. But before that, I have two questions for you. How many of you heard about Elasticsearch? Oh, cool stuff. How many of you are using Elasticsearch in your architectures? Great, thank you very much. So I'll be talking about big data and Bitdefender. What type of data are we storing, how we store this data, how we use it. And I'll end my presentation with lessons learned from implementing our systems for more than 8 years. So, my name is Octavian Rinciog. I'm a senior software engineer at Bitdefender for more than 8 years. I also have a PhD in computer science. If you want to reach me, that's my email account. So, what type of data are we storing inside our platform? First, we'll talking about event streams, where an event is something that happened in time t. And basically it's a piece of information with a time based. So in our systems we have two types of data. First we have telemetry data streams. All Bitdefender products are sending this kind of telemetry inside of our systems, and what telemetry means, it's something based on the product, something that happened on the product. For example, an user installed the product, an user uninstalled the product, an user disabled or enabled the feature, or all kind of activities inside the product. We don't care about the user. We anonymized all the user informations, and we do care only about our product. And having this type of data helped Bitdefender to become a data-driven company. Second, because we are a security data company, we receive a lot of security streams from our clients. And we have infections, we have spams, we have online threads, all kind of malware happen in all over the world. And third, we augment these data streams using our laboratories info and intelligence. For example, we are receiving an URL, we add the information if it's not infected or not. And we add several type of this kind of information using our intelligence. So, Our data is structured. We receive JSON from all our products, but we don't impose any schema. And actually, we are schema-less. Because we have multiple number of sources and it's not uniform, it will lead to difficulties down the line. And to solve this problem, we standardize field name across multiple data streams. We have origin and IP. We have HTTP file path, HTTP method, and stuff like this. Well, we also extract the semantic from the field. We know what if a field contains an URL, an IP, or a domain. In this way, we lose data generality, but we win data affinity, and I'll show you in a future slide where we used this kind of standardizations. Next, let's see how we store this data. First of all, our solution began a long time ago, 8-9 years ago, with the following requirements. Ingest some data streams from a number of sources, query them near real time, create historical stats from the gathered data, shows those aggregated stats in dashboard. So we looked on the market, we see what solutions was fit to us, and it seemed to go for the Elasticsearch stack. Right then in 2014, the Elastic just went from 0.9 to 1.1. So the Elasticsearch was very fast on searches. It can execute very near real-time aggregations, and it has a very nice user interface called Kibana, where you can visualize the dashboard. So we put for the POC a simple HTTP input API with Elasticsearch, which raw data in Elasticsearch, and the Kibana, which can query the Elasticsearch. It was a very simple architecture, and for the POC it worked right then 8 years ago. So in the following slides, I will show you how this simple architecture evolved during time and what changes have we done to scale. So we began with this simple architecture, HTTP API into Elasticsearch. Next, we found out that our data flow is not constant and it has spikes during rush hours. So we had to introduce a buffer between the HTTP API and the database. So we introduced this buffer, and it was implemented as a RabbitMQ databases. Of course, we also introduced the queue consumers. The buffer has the role to level the flow to the database. Next. Our HTTP API was largely adopted in our company and received data from multiple locations. But for some location, it had a big latency caused by the geographical distance. So we had to minimize this latency. So we had to distribute the API into multiple data centers. Of course, we had to put also the buffers in the data center. And using the shoveling feature from RabbitMQ, we gather all the data in the central data center, and we have the same consumer with which raw data in Elasticsearch. Next, we all worked okay until we had to introduce some custom asynchronous processing for the data streams. The problem was that with this processing was causing delays for the data streams. So if you kept all the data in one queue, the queue will have worked at the speed of the slowest data flow processing. So we had to split the queue into multiple queues, one for each data streams. And we also had to introduce the custom consumer with processing plugins for a subset of our data streams. Next, let's see how our Elasticsearch clusters are implemented. as I told you, we store this data in Elasticsearch. First of all, we had the simple architectures. I'm sure that most of you are aware of this infrastructure. Multiple nodes in one cluster with master, data, and query nodes, all having the same role. This worked okay until the input and the query rate grew. So we had to somehow scale horizontally. The nodes were suffering, but were suffering also the management clusters, because the master ingested data. So we split the nodes into dedicated nodes, the data nodes which receive all the writes, the coordinator which receive the queries and aggregation from the clients, and the master nodes who's only responsible for the management of the clusters. Next, we wanted to save streams for a longer period of times, and with the current resources we couldn't scale, so we had to move some shards on nodes with low resources. For this we split the architecture into hot, warm, cold nodes. The hot receive all the writes, the warms nodes receive the majority of the queries, and the cold has the most storage. So, how looks our infrastructure now? It's deployed in Kubernetes. For 3 years we deployed in Kubernetes. After we had virtual machines. After we deployed in Kubernetes, we are safe. Our hot nodes are having local SSD storage, and all the indices on these nodes are replicated by ones. We receive all the writes from the clients, and the number of queries are average. As for the CPU and memory, it has a lot of CPU and a lot of memory because they are doing a lot of indexing. As for the warm nodes, their storage are implemented on Ceph, and they don't have replicas. The indices, they don't have replicas, but all the data are replicated on the Ceph level. The majority of the queries are here. We'll show you in the future slide why. And the CPU, the memory, and the storage are average. As for the cold nodes, their storage are implemented on Ceph, HTA storage. They're having a lot of storage. And they don't have replicas, the indices. But the indices are replicated on the Ceph level, so we are safe from data view. They receive a small number of queries, and they have a lot of memory because they are on this type of nodes. There are a lot of shards. The coordinator nodes, their role is to run all the aggregations. The aggregation in Elasticsearch are very memory hungry, so they have to be memory and CPU with a lot of resources. So let's see how our index architecture looks like. All the data in Elasticsearch are kept in multiple indices. Back then, when we started this program, we implemented all the data in one big index. All the data streams are going into one big index. This was okay for the POC, and was done because the Elasticsearch version right then was permitting us. It was 1.1. Right now at Elastic 8, this can be done. For the POC worked okay, but the event rate grew, and we had to split that one big index into multiple indices, the one for each data stream. But we also this index also grew, And we saw that the queries were suffering because the indices and the shards were big. A query in Elasticsearch is faster when the shards are smaller because all the structure from the shards are smaller. So we had to split that original index into multiple indices, one for each type of nodes. The first one is the current index and it resides on the hot machines. And when that index can be rotated, I'll show you in the next few slides how it will move to the warm and to the cold nodes. So, what are our guidelines for rotation? It will be a very technical slide, so bear with me. Next, we have the current index. It's one for each data stream, and that index receives all the writes for the data streams. The number of shards depend on the rate of events, but it's always multiple of 2. So why? Here the rule is one shard cannot receive more than 2k events per second. It stays on the hot machines, and the index name is data stream and the creation timestamp. It has 2 aliases. One is data stream current, and the other is data stream. Next. When this current index reaches 100 gigabytes or different kind of rules, it's moved to the warm machine, to the warm machines, and there we apply some optimizations. We shrink it at 2 shards. All the Lucene segments in that shards are merged, and we compressed. In this way, we saved a lot of storage. The new index has in average 68% of the original, and we put more shards on the same node. We have custom warm time to live rules per data streams. Once that rule is coming to an end, it will be deleted or moved to cold nodes. It depends of the data stream. Its alias, it's a data stream, and we apply this alias schema in order to be able to query all the data from one data stream. So, let's look what is our current architectures. It look like this. A very big component. I won't describe any of the component, but what I want to emphasize is from the describe input architectures, the data goes to Elasticsearch clusters, where we have some Kibana with several custom plugins implemented by us. From this input architecture goes to a streaming architecture, where we have a custom stream processing. All Bitdefender employees can write a stream processing program which can interact with the streams. For example, they can do machine learning models, they can put data in other databases, or can run advanced analytics. Also, from these input architectures, we are sending data to another stream architecture when we have long-term storage solution implemented in Hadoop and Hive. And there we have a nice user interface called Apache UEM, which can visualize data from the HDFS. All the architecture is implemented in Kubernetes besides the HDFS. We didn't put it in Kubernetes. So, I want to tell you a few words about monitoring. For us, it was very, very useful and saved from a lot of debugging. All our components, no matter small they are creating metrics, And I don't talk about only about CPU, memory, storage, or stuff like this. We talk about relevant metrics to know what our application does. Our monitoring stacks compounds of two types of metrics. One is the push metrics in push to Graphite, and the other is pull metrics, Prometheus and Victoria metrics. As for the view alerts, we are using Grafana. Next, how we use this stored data. So, as I already told you, we have Kibana with several plugins implemented by us. This is a user interface. It's simple, it's easier to use for everybody. And we have tons of dashboards, alerting. We have a custom alerting framework implemented in Kibana. We also have a custom query language because the Kibana isn't enough flexible for us, but it's very easy to use for everybody. Next. When you want to do very advanced analytics, or you want to interact with the to the stream in real time, then you have to write some code. And we have the custom stream processing framework. All the Bitdefender employee can write a code and interact with the stream in real time or historical mode. It's more complex and requires more intimate knowledge about the data. Let's see what are the benefits from implementing these systems. First, by analyzing the collecting data, we can influence the business directions. We saw what were our product adoption, we saw what is the feature usage. We can analyze this, what are the competitors on our client machines. Second, we can support for avant-garde technologies and for new releases. When a new technology is released, we view the adoption progress, we analyze the results, and we can test some machine learning models from using our technology. Third is the foundation for creating new projects by bringing together same type of data from unrelated data streams. As I told you, we have some data standardizations, and we receive from multiple sources information about DNS data. The DNS domain is hosted on one IP, and with this information we build a passive DNS. Passive DNS is a collection of information about DNS resolutions. A domain is hosted in one IP at time t. It's very useful for the security investigations. When you have an incident, then you must know what was the state of the DNS when was that incident. So we build this passive DNS using the data from different data streams. Next, what were the lessons learned from implementing these systems for more than 8 years? First, scaling needs tweaks. For big clusters, the default settings are not enough and should be modified. Every technology has some kind of default settings, but the default settings are implemented for average cases. Second, you should monitor everything. No matter the small the components is, you should monitor everything because it's very, very useful. And you should implement some time to define your relevant alerts, because when something bad happens in our data architecture, data platforms, it's on one metrics that it's proven and showed. So you have to know what is the state of your systems. Third, there is no silver bullet technology that solves every problem. And there is a cost for everything, and you must know what is your use case. For example, if your use case needs very fast searches, then you can go to Elasticsearch and implement one Elasticsearch cluster. But if you don't care about speed, then you should choose another technology, because Elasticsearch is very hungry on resources. When implementing data architecture, think at 10 times your current data needs and scale horizontally, because eventually the data will grow. And you have to scale, and you have to have chosen the right technology before this. And last, be ready for changes, because all our data architecture, no matter great they are right now, they will change in a 1 year, 2 years, or something like this. So yeah, thank you for the presentation. Yeah, we are Bitdefender, we are Ferrari team partner. And during our presentation, no system has harmed, but we ingested over 2 million events and 200 gigabytes in 20 minutes. So thank you very much. If you have questions, yeah.
Really great presentation. Thank you. I want to ask about Elasticsearch since it's running Java. I'm wondering if you ever had issues with garbage collection poses, and what version of Java are you using for running Elasticsearch, and if you ever needed to tune the arguments for running the Java virtual machine. Okay,
very good question. Thank you. As I told you, we have run Elasticsearch for 1.1 to we are now at 7.9. Until the Elastic 5, including Elastic 5, we had to tweak the Java garbage collection. But after, we haven't done this because the default settings are good enough for us. And until Elastic 6, we had a lot of heap spaces, heap overflows. But after that, in 6, they resolve a lot of issues, and they are quite okay with the clusters.
Got it, thank you.
Thank you for the presentation again, very informative. Just wondering if all the scaling of Elasticsearch and logging and rotating indexes you have done with just the capabilities of Elasticsearch, or you did some custom programming in order to, and how much if it is custom programming, how much it costs, whatever that means, time, money, people, whatever.
Yeah. We have implemented all kinds of custom things for our needs. Our cluster is 200 terabytes, and we have more than 5,000 indices. And yes, we implemented a lot of things in-house. For example, the index rotation. For example, the ingesting is implemented in-house. We didn't appeal to any of Elasticsearch capabilities, such as logstash, such as index lifecycle management. We implemented the rotation before the index lifecycle management even existed. So we had this problem before even they know about it. So we implemented a lot of things in-house. But after we switched to Kubernetes, there weren't any of operational aspects that we need to know about. The Kubernetes saved us from a lot of operational time for this type of clusters.
I have a question regarding how do you keep the older data. So do you do some aggregation and keep the data aggregated for the, let's say, longer periods? And also, how do you put the data in Hadoop? You take the indexes as they are, or you put in other format regarding this storing of longer period?
Yeah, thank you for the question. We don't any aggregate the data for the historical part. We actually, on the cold nodes on the Elasticsearch, we have telemetry data nodes, telemetry data that we didn't aggregate them to put, just take the indices and put on the cold. As for the Hadoop, we put all the data in a Kafka, and we have a Kafka Connect which just throws data into HDFS with the HDFS connector. We don't do any aggregations. They are all raw data from the clients to the long-term storage. And in this long-term storage, we have a lot of security data informations.
Yeah.
Yes, so I have a question related to the fact that you mentioned that there is no index replication on some tiers of the storage. So my question here is, how do you deal with state changes on the actual Elasticsearch cluster? Because when you lose a node, you lose a node. It takes time to recover. How do you deal with those events?
Yeah, actually, we don't care a lot of our time to live, and our we can afford some downtimes. 2 minutes, we can afford the downtimes. So also the data is replicated in Ceph. As for the replications, yes, there is a cost, but Ceph is very low on resources than the Elasticsearch. So we had to introduce this kind of let's say a modification of our system, not to store the data in the Elasticsearch and consume all the resources that the Elasticsearch need to have on the cluster. So we move the data on the Ceph, it's low on resources, so we've done our job with that. But we can afford some minutes of downtimes.
Any other questions?
Yeah. Yes. Yeah. There are many types of Cephs, but yeah.
Any other questions? I have a question, if I'm allowed. From what I see in terms of use case, this is very, let's just put it like by the book, for a security operations center, you know, in terms of architecture. And my question is, did it morph in a product or in a technology used to serve SOC architecture? Or what's the, let's say, the best value that it brings in terms of technology or productization of it? What do you use it for the most? Let's put it this way.
We are using for the analytics part, and all Bitdefender employee can watch and to see what are the products feature, if it's used or not. And also we are using in the security part, and we are doing a lot of analysis of our infections, and we also discover a new way of the attack from analyzing this kind of data. So we have 2 parts of analyzing. One is the telemetry and the other is the security. And from the security part, we also discovered, as I told you, a new attack from this kind of data.
Okay, okay, great, thank you. If there are no other questions, ladies and gentlemen, please give it up for Octavian.
Thank you very much.